Hi, I'm Xu Wang, a PhD candidate from University of Science and Technology of China. It's an honor to be able to share our work, multi-graph fusion-based spatiotemporal dynamic learning framework with you here. We will introduce our work in the following 4 parts. Let's start with some background. In this work, we are interested in the kind of spatiotemporal data which consists of multiple time series collected from different sensors located at different locations. For example, we may have 4 traffic flow sensors located in a city, and they collected traffic flow data, which can be visualized as 4 time series. The spatiotemporal data we're interested in can be abstracted as a discrete function on a set of points, each of which corresponds to a sensor. In this work, we focus on spatiotemporal forecasting problem, which is defined as follows. Given historical data with t time steps, we wanted to learn a model of function f theta with parameter theta to predict future data for q time steps. The core difference between spatiotemporal forecasting and univariate time series forecasting is that in the scenario of spatiotemporal forecasting, there exists non-ignorable correlations among nodes. And many existing state-of-the-art works, for example, STGCN and the STFGNN, apply graph convolution to capture the spatial correlations among nodes and utilize static adjacency metrics to model the correlations. However, graph convolution has the issue of oversmoothing. Oversmoothing issue means that when the number of layers of GCN increases, the features of different nodes become similar and the representational ability of GCN becomes poor. Also, the static adjacency metrics utilized in existing works cannot capture dynamic correlations among nodes. And the dynamic correlations among nodes are common. For example, traffic patterns are different at 8 o'clock in the morning and 12 o'clock at noon. We proposed our model to tackle both the aforementioned issues, oversmoothing and the dynamic spatial correlations. To capture the dynamic dependencies among vertices, we propose a dynamic neighbor searching module to dynamically determine neighbors of each node. For each node, we learn time-specific weight metrics and determine the dynamic correlations according to the product of features of other nodes and the weight metrics. As illustrated in this figure, at each time step, we have weight matrix W and node feature V. Then we determine the adjacency among nodes by the product of V and W. Such operation leads to dynamic adjacency matrix at different time steps. We find the oversmoothing issue of GCN results from the message passing strategy among nodes and the data flow between layers. Thus, we propose adaptive heterogeneous representation module, which applies attention and gated mechanism for tackling oversmoothing issue. The message passing strategy of vanilla graph convolution is aggregating nodes according to certain weights. The weights like A12 in this figure are prefixed, which leads to similar features of nodes when the network goes deeper. Therefore, we propose an attention-based aggregation strategy among neighboring vertices. The calculation is shown in the lower left corner. As seen, attention mechanism allows us to have data-driven weights and thus alleviate over-smoothing issue. Also, since vanilla GCNs directly passing features among layers, changing the data flow between layers can certainly alleviate over-smoothing issue. We therefore propose a gated mechanism-based data flow between layers. The calculation is similar to LSTM. We initialize memory aim with the original node features. Then we compute a forget weight and an update weight. The memory and the final output fed into next layer are computed based on the two weights as in the formulas. We combine the above two modules, DNAs and AHR, as illustrated in this figure. For given spatial temporal data G that corresponds to P historical intervals, the DNAs module calculates dynamic adjacency metrics for constructing feature graphs at each time interval. Then the feature graph and the original structure graph are fed into AHR module for extracting spatial patterns. The multi-graph fusion module further fuses the outputs of AHR module for both graphs by applying a fully connected layer on the concatenation of the two branches. And the fusion results are taken as input by DVR module for generating prediction. Next, we detail the DVR module. DVR module takes advantage of differential information to enhance modeling temporal correlations. Specifically, DVR first applies one-dimension convolution on the feature of nodes, then computes the differential information of the convolved features. Then the differential features are combined with the original input feature to generate a weight eta, which is used to weighted some differential features and the original features. We evaluate our model on 6 real-world spatial temporal forecasting datasets. As can be found in this table, compared with several state-of-the-art methods, our model achieves either best or second-best forecasting accuracy with respect to all 3 metrics on the 4 datasets. We also evaluate our model on another 2 datasets with the same metrics. And the results are the same. All the results prove the superiority of our model on spatial temporal forecasting problem. We also evaluate the effect of proposed AHR module on over-smoothing. 2 metrics are used. A group distance ratio mirrors the ratio of intergroup distance over intragroup distance in Euclidean space, and a small group distance ratio leads to the over-smoothing issue, where all groups are mixed together. Instance information gain represents how much input feature information is contained in the final representation, and the over-smoothing issue would lead to a small value of instance information gain. For both metrics, higher is better. We can find when the network goes deeper, the proposed AHR certainly has positive effect on alleviating oversmoothing issue. The table below shows the effect of different components of our model on forecasting performance, and we can find all the proposed modules contribute to the superiority of our model. We finally conclude our work. In this work, we propose a DNS mechanism to select the most important neighbors from the entire graph. We design adaptive heterogeneous representation to reduce redundancy in spatial perspective by filtering irrelevant embedded feature information. We propose a novel temporal differential vertex representation module to take temporal differential information among intervals into account. Extensive experiments on 6 real-world cross-domain and cross-city datasets demonstrate the superiority of our proposed method. Thanks.